Ayan, so recorded naman yung ating session. Okay, so ayun na nga. So yun, simulan na natin to, no? Para ano. Okay. Raise hands lang pagka ano, raise hands lang pagka ah, may audio Pagka may audio yung plinay natin mamaya, pa-raise hands na lang. Okay? Okay. So far we have covered out of this design objectives ng control systems which we have enumerated at the start of this at the start of this course. We have may audio ba? Wala nag-raise hand. Sabi ko pag may may audio, dinig niyo yung audio ng video. Okay, so sige. So far covered one, okay, which is to produce the desired transient response. Okay. Now, in the next two topics, okay, in the next two sections, okay, we will cover now yung stability at saka yung steady state error. Okay. So in this case, we will first cover yung stability. Okay. And then on the next section, we will cover steady state error. Okay. So stability is the most important specification. Okay. So we should remember that without stability, okay, or without ensuring first that your system is stable, your system design is basically moot and academic. Ibig sabihin, walang silbi yung efforts natin to design the transient response and the steady state error kung unstable naman yung system niyo. Okay? So, before a control systems engineer analyzes a system for transient response and steady state error, he or she should be first concerned about the stability of the system. Okay, so basically, ang proseso talaga bago tayo dapat makapag-analyze is we first ensure na stable yung system natin. Okay. So far, dun sa ating transient response or nung kinover natin yung transient response, we are assuming that your system is stable. Okay. And in fact, kapag naman tinest nyo lahat yung systems natin before, okay, we are assured na stable naman talaga siya. Okay. Pero, ang totoong proseso talaga niyan is dapat we have to ensure first that your system is stable before you actually proceed analyzing the transient response and steady state error. Okay. Then as engineer moves to design the system for desired transient response and or steady state error, okay, he or she should have an idea of the extent of the changes on system parameters he or she can make to keep the system stability. So habang dire-design nyo naman, okay, so dun sa analysis part, kailangan tingnan nyo muna kung stable yung system bago nyo siya i-analyze for steady state response and for transient response and steady state error. Sa design part, habang nagde-design kayo, kailangan ini-ensure nyo na yung changes dun sa yung gagawin yung mga changes dun sa system parameters would keep the system in its stable state. Okay, otherwise, kapagka nakuha niyo nga yung transient response na gusto niyo, pero nung pinalitan niyo naman yung system parameters niyo, bigla siya naging unstable, then wala ring silbi yung dinesign niyo. Okay? Now, in this section, we will define stability. Okay? Study a tool to analyze the stability of systems and design system parameters and transfer functions that will keep the system within its stable condition. Okay. Now, at the end of this lesson, you should be able to 1. Define stability and explain the necessary conditions that makes a system stable, marginally stable, and unstable. 2. Make and interpret a route table. Okay. The basic one, the first row element is 0, or the entire row is 0 to determine the stability of a system. And determine the range of values allowed for a system parameter to keep the system within a stable region of its operation. So ito yung ating lesson outcomes. Okay. In the discussion of time response in the previous lesson, we have stated that the time response of a system has two components. Okay. So we have the natural response and the forced response. Okay. So that we say that the total response is the forced response plus the natural response. Okay. So we also have emphasized in the previous discussion that full control. Ibig sabihin kapag yung system ninyo is under a state na nakokontrol talaga natin siya. Okay. Is achieved if the steady state response of the system has the same form of the output. Meaning, kung ang ating input ay step, dapat ang ating output should be, kung ang input natin ay step, dapat ang output natin should be a constant, or has a constant steady state response. Okay, and so on. Okay. Pero possibly of different magnitude. Okay, so pwedeng iba yung level niya. Okay. Thus, for a full control, okay, the natural response should decay to zero. Okay, so kailangan itong ating natural response na to, okay, itong ating natural response na to should decay to zero kapag nagaan tayo, nagkakaroon tayo or kapag ang system natin is under control. Okay. Now, from there, doon natin malalaman or doon natin madederive yung definitions ng stability, ng instability, and marginal stability. So, bali, in terms ng stability, meron tayong tatlong states. Okay? Whether your system is unstable, okay, or yung state of instability, okay, meron tayong system na stable, okay, at meron tayong system na marginally stable o yung system natin na nasa state ng marginal stability. Okay? So, an LTI system is stable. Okay? An LTI system is stable if the natural response approaches zero. Okay? As time approaches infinity. So, alam na natin yan. Dapat mag-approach ng zero yung natural response natin as time approaches infinity para masabi natin na yung system natin ay stable. Now, if otherwise, if the natural response grows without bound, okay, as time approaches infinity, then you can say that your system is unstable. Okay? And then finally, an LTI system that is marginally stable, okay, pag sinabi nyo ang system niyo ay marginally stable, if the natural response neither decays nor grows, but remains constant, okay, or oscillates as time approaches infinity. Kung ang kung ang natural response niyo mag-oscillate after some time, okay, at nananatili, at yung oscillation naman niya has a constant amplitude, okay, o kaya kung hindi man siya nag-oscillate, magme-maintain siya ng isang constant value, okay, then your system is said to be marginally stable. Yung natural response lang pinag-uusapan natin. Okay, so ayun, yun yung tatlong definition ng stability. But this is based on the behavior of your natural response, which madalas hindi natin talaga to madederive with direct measurements. Okay, kasi ang ma-measure lang talaga natin is total response. Okay, so we would not be able to measure this directly. Okay, hindi natin siya ma-measure ng directly kasi natural response yung pinag-uusapan, o natural response yung ginagamit as a basis of definition of stability. Okay. A better way, a more practical way to actually measure yung stability ng system niyo is actually to look for the total response. Okay, kasi pag nag-measure tayo ng response, mas nakikita natin, okay, or mas measure natin directly yung total response ng system niyo. Okay. Now, obviously, kung titingnan natin yung total response, tapos alam nyo na yung input nyo is bounded. But when you say an input is bounded, it means na yung value nung input ninyo has a certain finite value. Okay? So, hindi man siya magstay dun sa finite value na yun. At least hindi siya lumalagpas dun sa finite value na yun. So, you say that your input is bounded. Example ng mga bounded input is yung delta t. Okay? Example natin is yung delta t. Okay? Example din natin is yung step function. Okay? Example na natin step function. Okay, and then example din natin is yung sinusoidal function. Okay. Yan. Yan yung mga example natin ng ano, ng mga bounded input. Yung ramp, okay, yung ramp function natin at saka yung parabolic function natin. Okay? Yan. Yung ramp function natin which is at t, u of t. These two are unbounded inputs or unbounded signals. Kasi yan ay tumataas as your t approaches infinity. Okay. So itong tatlo, itong delta t, itong u of t, at saka itong sinusoidal natin. These are bounded inputs or bounded signals. Okay. So ngayon, kapag yan ang in-input ninyo, okay, if you have an input of delta t, u of t, or sin u of t, okay, and your total response, okay, and the total response does not approach infinity as time approaches infinity. Ibig sabihin, hindi umakyat sa isang unbounded value yung total response nyo. Okay. Then, we can say that the natural response is not approaching infinity and thus the system is stable. So, obviously, kapag ang pag ang input nyo ay bounded, at you are expecting na dapat ang output nyo is also bounded. Okay, para masabi nyo na yung system niyo ay stable. Okay? Otherwise, kung ang input nyo ay unbounded, okay, obviously, yung total response nyo should also become unbounded. Okay? Kaya lang, in that case, hindi natin masasabi ngayon kung nag-decay ba sa zero yung natural response ninyo. So therefore, wala tayong conclusions dito. Okay? Basta sigurado tayo, kung bounded yung input, dapat bounded din yung output. Yun yung sinasabi natin. Okay? Pero kung unbounded yung input, hindi natin masasabi ngayon kung stable. Hindi natin masasabi ngayon kagad outright kung stable yung system nyo o hindi. Okay? So from this, we can define now stability based naman sa relationship ng input at saka ng output ninyo. Okay? So a system is stable if every bounded input yields a bounded output. Okay? We call this the BIBO, bounded input, bounded output stability requirement. Okay? So kapag bounded ang input, dapat bounded ang output. Your system is stable then. Okay? Now, a system is unstable. Okay? If any bounded input, okay, yung input nyo is bounded. Okay? Pero, it yielded an unbounded output. So, yung output niyo ay tumaas without limit. Okay? So, therefore, in that case, you can say that your system is unstable. Okay? Now, a system is marginally stable if it is stable for some inputs and unstable for others. Okay. So, actually, ang medyo mahirap i-interpret yung marginal stability kapag output yung tinitingnan. So, um, we will have some alternative definitions. Kaya kapag talaga nagde-define tayo o nag-aantay ng stability ng system natin, we actually look at the signals. Okay, we actually look at the input and output signals, and then we actually inspect yung natural response kung kaya natin siyang i-isolate para malaman natin kung siya talaga ay stable o hindi. Okay. Pero again, ang pinakamagandang sign na ang system niyo ay stable is if it follows the input. Kung sinusundan ng output, okay, kung sinusundan ng output ng system niyo yung input, okay, and then you were able to achieve a full control, then you can say that your system is stable. Okay? So, kung halimbawa ang system niyo ay kung ang input niyo ay sinusoidal at ang output niyo naging sinusoidal din, then more or less stable yung system niyo. Yun nga lang, di natin masabi kung siya ay stable or marginally stable. So, doon lang medyo magkakaroon ng konting confusion or konting ambiguity. Okay. So, ayan. Now, how can a system be concluded as stable? So, paano ba natin nako-conclude na stable yung system natin? Okay. Looking into the natural response, which is required to approach zero as time approaches infinity, it can be seen that the system poles that yield the natural response should be negative. Okay, if they are real or have negative real parts if they are complex. Okay. Obviously, yung system poles ninyo that yield the natural response, dapat magde-decay siya sa zero. So therefore, kung real pole man siya, dapat negative siya. Dahil magkakaroon kayo ng yung ano na yun, um, yung pole na yun would actually generate an exponential that has a negative exponent. For example, kung meron kayong expression or meron kayong kung isa sa mga partial fraction decomposition ng system ninyo or ng response ninyo would be A over S plus sabihin natin 4. Okay? Pag ito in-inverse ninyo, magiging E raised to negative 40 yan. Okay? So kapag ito, kasama ngayon to sa natural response niyo, obviously, itong E raised to negative 40 would decay to zero. Okay? Otherwise, kung ang nakalagay sa partial fraction decomposition niyo is A over um, S S minus 4, okay? Ano to ng inverse Laplace transform na A over ng A E raised to 40. At yung AE raised to 40 na yan, okay, sorry, hindi niyo pala nakikita. Ayan. So, halimbawa kung meron siyang partial fraction decomposition na A over S minus 4, pag in-inverse niyan, magiging AE raised to 40 yan. Okay. And obviously, itong AE raised to 40, alam natin na ito, magkano yan? Hindi yan magdidecay, but rather, mag-i-increase yan to infinity. Okay. So therefore, that would render your system to be unstable. Okay. Ganun din kapag meron kayong complex exponential, complex poles. Okay. So halimbawa, meron kayong AS plus B over S plus sabi natin 2 square plus 4. Okay. So kapag in-inverse nyo yan, it would have something like e raised to negative 2t times cosine 2t plus a cosine 2t plus b sine 2t. Okay? So, alam natin na since ito ay negative, kahit na meron kayong sinusoidal dito, magdidecay yung dalawang sinusoids na yan because you are multiplying it with a negative exponential. Okay? Whereas, kung magiging positive siya, kung magiging positive ito, then we can say na hindi ito magdidecay to zero, but rather mag-i-increase yan to infinity as your time approaches infinity. Okay? So, yun yung requirement do sa mga poles natin. In terms ng positioning ng poles sa S-plane o sa complex S-plane, we need these poles to be in the negative side. Okay? So, yung sinasabi nga natin before na dapat nasa left half plane siya. Or dapat lahat ng system poles niyo nasa left half plane. Okay? So, stable systems have closed-loop transfer functions with poles only in the left half plane of the complex S-plane. Okay? So, dapat yung closed-loop poles ninyo, okay, are in the left half plane of the complex S-plane para siya maging stable. Okay? Those systems with at least one closed-loop pole that is on the right half plane, at least kahit isa lang. Okay? At least one. Okay? They are deemed to be unstable. Kahit isa lang at kahit konting-konti lang yung pagka-positive niya. Ibig sabihin, kahit 0.1 lang yan. Yung pole mo is at 0.1, basta positive, your system is rendered unstable. Now, systems whose closed-loop poles, okay, that are on the j omega axis, meaning andun siya mismo sa boundary ng left half plane at right half plane, and multiplicity of 1 are marginally stable systems. Okay? So, kung meron kayong system na halimbawa ito yung niyo, sorry. kung meron kayong ah, so ito yung natin, S-plane natin. Tapos meron kayong pole dito sa ating J omega axis. This is your J omega axis. Okay. Kung meron kayong pole dyan, tapos ang multiplicity nila 1, okay, you can say that your system is marginally stable. Okay. Pero kung nag-double pole siya at the same position, hindi na stable yan. Okay. So this renders your system to be unstable already. Pagka nag-double pole siya dun sa same position sa J omega axis. Okay. Kasi yung mga ganyan, yung mga ganyang mag-ano yan, mag-yield yan ng inverse na t sine o kaya cosine omega t. Okay. And may t na to, this t increases as your time increases. Okay. So therefore, this is an increasing function. Okay. So yung system na halimbawa, meron kang pole dito, tapos meron kang pole sa left half plane. Okay. This is considered to be marginally stable. Okay. So as long as meron kang pole dun sa ating J omega axis. Okay. This is considered to be marginally stable. Basta wag lang sila mag-double pole. Kahit marami sila diyan. Halimbawa, meron pang isa dito. Okay. Meron pang dalawa diyan. Okay. Marginally stable pa rin 'yan. Basta wag lang sila magdo-double pole dun sa isang location. Okay. So ayan. So we have here an example of systems na na we have here an example of systems na stable tsaka unstable. Okay. So yung system niyo na stable, pag nilagay niyo sa closed loop transfer function. Okay. Remember dapat ito gawin natin tong closed loop transfer function. Okay. So magiging 3 all over s times s plus 1 times s plus 2 plus 3. Kailangan maging closed loop yan. Tapos kukunin natin yung poles niyan, in which that would give us this one. Okay. So makikita natin yung tatlong poles natin, ito, tsaka ito. These are on the left half plane. So we are ensured na yung system ninyo ay stable. So magre-return niya ng system na under-damped, and at the same time, alam natin may full control. O meron tayong full control dun sa ating system. Okay? Kasi susundan niyo yung input ninyo na step input. Okay, so this system is stable. Otherwise, ito, okay, again, i-reduce natin ito sa kanyang closed loop form. So this becomes 7 all over s times s plus 1 times s plus 2 plus 7. Okay, tapos pag kinuha natin yung poles niyan, okay, we will have the following. We will have the poles here, tapos ito. Okay, meron kayong dalawang poles dun sa right half plane. Okay, meron kayong poles dun sa right half plane. So therefore, the system is unstable. So may verify niyo yung pag renap nyo, makikita nyo na yung signal niyo lumalaki as your time progresses. So we will say that this system now is unstable. Okay. So ayan. Now, determining the stability of feedback control systems is not as simple as that, however. Some systems will have higher ordered faults when reduced to an equivalent closed-loop transfer function, which requires factoring and solving for the roots of the denominator of the transfer function. Pero sa atin, in the presence of computing tools such as MATLAB and Octave. Actually, hindi na masyado mahirap para sa atin 'to. Okay, kahit na meron kayong 10 poles. Okay. Kayang hanapin niya ng MATLAB tsaka ng Octave. Okay, masosolve ng MATLAB yung 10 poles na 'yan kapag meron kayong gamit na MATLAB tsaka Octave. Okay. Kaya lang still kapag nagde-design tayo, hindi natin magagamit yung MATLAB tsaka Octave kasi there is this system parameter na kailangan nating palitan ng value in which hindi siya directly may evaluate ng MATLAB at saka ng Octave unless i-program natin siya to do just that. Okay. So, this motivation of us na kahit na meron tayong tool to compute for this polls. Okay. Ah, kailangan pa rin nating aralin yung tinatawag nating tool. Okay. We will study in the next lesson. Yung tinatawag nating route Hurwitz criterion, in which that tool enables us to determine yung state of stability ng system natin. Okay, without actually computing for the location of the poles ng ating system. Okay. Now again, ang motivation natin to study that tool is not hinge on the fact na gusto talaga nating malaman yung stability ng system natin, but rather on the design side. Okay, well, we can use that to determine yung range of values for our system parameters so that we will maintain yung stability ng system natin at malalaman natin kung kailan siya magiging unstable. Okay. So, ayan.
Okay. So that covers yung first part na yun, that covers yung definition ng stability. Okay. So again, i-recall natin na define natin yung stability in terms ng natural response, okay, at saka in terms ng total response. Okay. Again, ano yung requirement natin sa natural response para masabi nating stable yung system natin? What do we require for our natural response so that we can say that the system is stable? Anyone? May tao pa ba dyan? Raise hands nga kung dyan pa kayo. Ayun. So, sige. So, sabi ni Miss, ano na yun? Wait lang ah. Saglit lang. So, pag yung natural response daw should approach 0. Okay? If your natural response approaches 0 as time approaches infinity, masasabi natin na yung system natin ay stable. Okay, so tama yun. Tinitingnan natin na stable ang system ninyo kapag ang natural response nyo nag-approach ng 0. How about in terms ng total response? Paano natin masasabi na yung system ninyo is stable kung ang titingnan natin ay total response? Nasa left lane yung poles. Ang tinatanong ko is in terms ng total response, hindi in terms ng location ng poles. Okay. Yung sinabi kasi ni Ms. Tampol, depende yon or masasabi natin na stable yung system natin kung nasa left half plane yung poles natin. That's in terms of location of the poles. Pero how about, how do we say na stable yung system ninyo kung ang pagbabasihan natin ay yung total response. So, depende kasi sa depende kasi sa kung anong gusto nating tingnang perspective. So, sabi ni Mr. Dasalia, kapag bounded inputs po, sir, and when the natural response is not approaching infinity. So, in terms pa rin na natural response yung second statement mo. Pero may sinabi ka dito na kapag bounded yung input. Ano dapat ang ni-expect nating output kapag bounded yung input? Para masabi nating stable siya. So, kapag bounded yung input, anong expectation natin dapat sa output para masabi nating stable siya? O dun sa total response, ano dapat siya? Pag bounded yung input. Anyone? Ginamitan pa nga natin ng ano yan, ginamitan ko pa ng ano yan, ng acronym para mas madali siyang matandaan. So pag bounded yung pag bounded input, bounded output. Pag ang input nyo ay bounded, dapat output yung output nyo bounded din. So yun yung tawag nating bounded input, bounded output requirement or BIBO requirement. Okay? So in terms ng total response or in terms ng total output, titingnan natin na stable ang system niyo kapag ang kapag ang output nyo ay bounded for every bounded input. Okay? So that's how we define yung ating stability in terms ng natural response at in terms ng output. Now, and again, in terms ng location ng poles, sasabihin natin na dapat lahat ng poles ninyo dapat lahat ng poles niyo ay nasa left half plane. Okay? At wala kayong pole na nasa right half plane. Okay? So that's how we say na stable yung system niyo. And ayun, yung next lesson natin would actually be dealing with a tool called the Routh-Hurwitz criterion para ma-identify natin kung stable yung system niyo o hindi or kung marginally stable siya. Okay? But this Routh-Hurwitz criterion basically does not tell you kung ano-ano yung mga poles. At ang sasabihin niya lang sa iyo is kung ilan yung poles na nasa right half plane. Okay? So, ayun. So, aralin natin tong Routh-Hurwitz criterion using this recorded video. Okay. Now, we proceed with the determination of the condition of the stability of your system. Pero this is aside from actually obtaining yung poles or yung location ng poles ng system niyo. Kasi nga ang ano nga natin is that we can actually solve for the poles using yung ating computational tools such as MATLAB and Octave. Pero kapag ka-design, medyo may hirapan tayo na gamitin yung mga yon. Okay, dahil nga ang unknown natin is the system parameter and ang kailangan ninyo para ma-solve yung mga poles na yon is the system parameter. Okay, so this Routh-Hurwitz criterion is very useful dun sa part ng design. That is why in spite of the presence of computational tools, okay, we need to study this tool pa rin. Okay.
So there's a method by which the stability of feedback control systems can be determined without actually solving for the roots. Okay, using the route Hurwitz criterion for stability, we can tell how many poles are in the left half plane, the right half plane, and on the j omega axis. Okay, so yun basically yung ginagawa ng yun basically yung ginagawa ng route Hurwitz criterion. That is, it helps us to determine kung ilan yung poles na nasa left half plane, ilan yung poles na nasa right half plane, ilan yung nasa j omega axis. Okay. Now, the method of the route Hurwitz criterion requires two steps. Okay. So number one, we need to generate a table called the route table. Okay. And number two, interpret the route table to tell how many closed loop poles are in the left half plane, the right half plane, and on the j omega axis. Okay. So paano ba tayo mag-generate ng route table? Okay. So for a closed loop transfer function na binigay sa atin dito, for example, sa figure 5.2. Okay. Ito yung magiging niya, ito yung magiging route table niya. Okay, ito yung magiging route table niya. Okay. So unang-una, kailangan naka closed loop. So meaning dapat naka single block lang siya. Okay. So remember that this should be a single block. Okay. So ayan. Now, number two, dapat yung denominator nyo naka polynomial form. Ang kailangan lang naman natin dito basically is the denominator. So kailangan yung denominator ninyo naka polynomial form. Okay. So now, when you are preparing for or when you are writing out yung inyong route table, okay. So gagawa muna kayo ng mga rows, okay. Ng mga rows that corresponds to to the powers of S. So magsisimula kayo dun sa pinakamataas na power ng S, which is S to the fourth in this case. Okay. Tapos S cube hanggang S raised to 0. So yun yung constant. Okay. Now, yung coefficients ngayon, okay, the coefficients ngayon ilalagay niyo dito. So ang arrangement is ito yung coefficient para sa S to the fourth, ito yung coefficient para sa S cube, ito yung coefficient para sa S squared, ito yung coefficient para sa S, tapos ito yung coefficient para sa constant. So, kung meron pa nang iwan na isang space, consider that to be 0. Okay, and in fact, yung iba pang entries nung dito is also 0. Okay.
Naintindihan yung initial layout. Okay. So, hopefully maliwanag yung yung first part na yan kasi diyan mag-uumpisa yung route table ninyo. Pag yan ay hindi natin nakuha, yung part na yun ay hindi natin nakuha, mahihirapan tayo mag-generate ng route table. Okay? May questions ba regarding dito? Okay. So, let us continue.
Okay. So, ayan. So, that's initially, yun yung
May question ba, Mr. Villacorta? Sige, habang hinihintay natin yung kung may question na si Mr. Villacorta, let's continue.
yan yung layout ng ating route table. Okay. Then, how do we proceed with the computation or how do we complete this route table? Okay. So, para ma-complete natin yung route table na yan, ganito ang computation. Okay. So, we start with yung third row kasi nandun tayo sa kanina. So, na-complete natin yung first two rows. Okay. So, dun tayo sa third row. So, determinant ito or negative, take note negative determinant ito ng A4, A1. Okay. So, ito. Okay. Ito. Tapos ito. Okay. Then, ito. Tsaka ito. So, negative determinant siya nun. Okay. Divided by A3. Okay. So, ayan. So, that will be your B1. Okay. So, meron magiging B1 yun. Okay. Ito naman, yung next column naman natin is ito. Okay. Ito. For the first column of your determinant. Tapos ito. For the second column. Divided by A3. Okay, so notice na dito, okay, yung ating second column, okay, is basically yung preceding column nung ano ninyo, ay yung next column nung ini-evaluate niyo. Pero yung first column niya, constant na ito. Okay, so that is why, ito, para ma-evaluate nyo to, so again, constant yung first column, okay, pero ito, should have been from here. Kasi wala naman ang entry dito sa 0 and 0 na siya. Also, the denominator is constant. Okay, so ang iniiba natin is yung second column. Okay, yung iniiba natin sa second column. So, halimbawa, dito rin. Okay, dito rin. So, this is A3, B1. Okay, so A3 at saka B1. Okay, so ito yung first column ninyo. Tapos yung ito, A1 tsaka B2. A1 tsaka B2, ito siya. Okay, which is yung next column ninyo. Okay, tapos ang divisor ninyo dito is basically B1. And don't forget that this is the negative determinant. Okay, so ito ganun din. Constant ito, yun pa rin yung first column ninyo. Then ito, okay, is 0, 0 kasi 0 na to, tsaka 0 na to. Okay. So again, constant itong B1 as your denominator. And so on. Hanggang sa matapos nyo yung row ng, yung row ng S raised to 0 or yung row ng constant. So, dyan matatapos ngayon yung pag-evaluate nyo ng route table. Okay?
Naintindihan yun? Yung part na yun? Kung paano natin tatapusin or paano natin kukumpletuhin yung route table. Okay, so dalawa lang yung medyo nakano. So, baka medyo malabo pa sa inyo. So, siguro para mas maging malinaw, yung example, tingnan natin. Okay, kasi baka mas malinaw to pagdating sa example.
So, let's have an example para dito sa ating system na to. Okay. So, first, natin siya. I-express natin siya as a closed loop transfer function, which in this case, this should be T of S equals 1,000 over S plus 2 times S plus 3 times S plus 5 plus 1,000. Yan. Or kung i-expand natin ito, this is basically, so multiply natin siya dito, no? So S plus 2, S plus 3, this is S square plus 5S plus 6. Okay, then multiply natin with S plus 5. So this is S cube plus 5 plus 5, so that's 10s square. Okay, 10s square plus 6 plus 25, that's 31s. Okay, plus 30 plus 1,000, so 1,030. So ito yung magiging denominator nito, no? Okay, so S cube plus 10s square plus 31s plus 1,030. Okay, so yun yung ilalagay natin doon sa ating route table. So, pag ginawa natin yung route table na to, okay, para dito, we will have these rows. Okay, so S cube, S square, S at saka S raised to 0. Okay, so ito ngayon yung coefficients natin, 1, tapos 10, tapos 31, at saka 1,030. Okay, and then of course dito 0 na yan. So pwedeng hindi niyo na ilagay ito eh. Okay. Now, it is a rule, ang allowed sa route table ninyo na mag-divide kayo ng positive number in any of the rows. Okay. Ang purpose nun para mas lumiit yung number ninyo. Okay. So, pwede kayong mag-multiply or mag-divide ng positive number sa isang row. Okay. So, in this case, yung ginawa dito is, so 10 ito, tsaka 1,030. Nag-divide siya ng 10. Okay. So, 10 divided by 10 becomes 1. Tapos, 1,030 divided by 10 becomes 103. So, allowed yun. Okay. Basta may divide nyo siya yung entire row ninyo. Okay. So now we compute now ito. Okay, as 1 times 103. Okay. So ito that becomes negative 1 times 103. 103 minus 1 times 31 divided by 1. Ito 'yun. Okay. So that's 103 minus 31. Okay. That's negative nun. That's divided by 1. That should be negative 72. Okay. O kaya actually ang ginagawa ko dito is para hindi ko na masyadong minamind yung hindi ko na masyadong inintindi tong negative na to. Ang ginagawa ko dito is baliktad. Ginagawa ko tong 1 times 31 minus 103 times 1 times 1. So ginagawa ko na siyang 31, ginagawa ko na siyang 1 times 31 minus 103 times 1 divided by 1. Kumbaga binabaliktad ko na tong dalawang to para hindi ko na i-account tong negative na to. Okay, so yun yung isang technique na ginagawa ko pagka nagko-compute tayo ng route table. Okay? So doon na nga lalabas yung negative 72. Okay, so dito naman this is 1 times 0, so that's 0, tapos minus 0 times 1. Okay? So teka, 1 times 0, parang mali ito. 1 times 0 kasi ito, dapat actually dapat 1 to eh. Ayan, dapat 1 to. Hindi yan 0. Ayan. So 1 times 0 dapat. 1 times 0 minus 0 times 1. Divided by 1. So 0. Ito rin. 1 times 0. Okay. So 0 na to. So negative 72 ito. So ito. Yung negative 72. Okay. Then, next is, dito tayo. So I'll have negative 72 times 103. Okay. Minus minus 1 times 0, 1 times 0 divided by negative 72. Okay, so that should become 103. Okay, so magiging 103 na siya. Ito. And then of course, 0 na to, 0 na to. Okay, so ang advice ko sa inyo is kapag ka 0 naman, huwag nyo nang ilagay yung 0 kasi mapupunulan ng 0 yung, yung route table niyo. So ang ilagay nyo lang is yung mga non-zero. Okay, so kapag ka sinulat natin yung route table natin, pag sinulat natin yung route table natin, so this is S cube. So, ayan, kapag ka tinanggalan natin yung pag tinanggalan natin yung mga computations natin, yan yung mabubuo yung route table. Okay. So, another technique na pwede kong ituro sa inyo kapag ka nagko-compute kayo is ganito. Usually, or lagi naman, kapag ka ito ay 0, halimbawa 0 na to, no? 0 na to. Lalabas, itong nasa ilalim nitong negative 72 na to is ito na siya. Kumbaga, pwede nyo ito, dali na kagad dito. Basta 0 yung nasa ilalim. So, meron kayo dito, dito, tsaka dito, tapos 0 to. Okay. Automatic na yung magiging sagot dito is ito. Okay. Pwede nyo namang prove yun mathematically. Pero, yun na yung isa sa mga technique na natutunan din natin habang, habang ginagamit natin yung route table ng paulit-ulit. Okay. So, ayan. So, ito na yung kompletong route table natin. Okay. So, what is next after we are done with the route table? Okay. So, this is now the time that we will have to interpret yung basic route table. Okay. So, the basic route table applies to systems with poles in the left half plane and the right half plane. Okay. When you say basic route table, ito yung walang mga zero sa first column. Okay. So, mamaya i-discuss natin yung mga cases na meron kayong zero sa first column at saka yung entire row ninyo magiging zero. Okay. Those are the two special cases of the route table. Pero in this case, we are dealing with a route table na basic pa lang. Okay. So, simply stated. Okay. Simply stated.
Class excuse lang sandali ano lang tayo, 2 minutes. Bigyan niyo ako 2 minutes Sandali lang. May anin lang ako. Okay, sandali lang. Hello, andiyan pa kayo? Okay. So, ayun. So, hopefully, nakukuha nyo kung paano yung, yung pagko-compute. Later on, may mga examples pa naman dito para makita nyo talaga kung paano kino-compute ng buo yung route table. Okay? And at this point, i-interpret na natin siya. Okay? So, listen carefully kung paano siya ni-interpret. Okay? Uh, the Route-Hurwitz criterion declares, ito yung Route-Hurwitz criterion talaga. The Route-Hurwitz criterion, sorry, uh, the Route-Hurwitz criterion declares that the number of roots of the polynomial, okay, of the polynomial that are in the right half plane, okay, is equal to the number of sign changes in the first column. Okay, again, the number of roots of the polynomial that are in the right half plane, okay, is equal to the number of sign changes in the right or in the first column. So, ang gagawin natin is pipilangin natin kung ilang beses nagpalit ng sign sa first column yung inyong route table. At yung number of sign changes na yun would actually equal to the number of um, roots or number of poles na nasa right half plane nung complex explain niyo. Okay, so balikan natin to. Bibilangin natin dito ngayon kung ilang sign changes meron siya. So, when say sign changes, yung positive naging negative o yung negative naging positive. So, halimbawa ito, from here to here, positive to positive. So, hindi to bilang. And then, from here to here, positive to negative. So, that's one sign change. Okay? And then, from negative to positive, that's another sign change. Okay? So, yung number of sign changes natin, okay, the number of sign changes that we have is 2. Okay? That also means that the number of poles in the right half plane for this system is actually 2. Okay? And since kung titignan natin, meron tong tatlong closed loop poles kasi S cube yung pinakamataas eh. Okay? So if we have 3 closed loop poles, okay, yung dalawa doon nasa right half plane. Okay, yung isa ngayon automatic nasaan na yun? Nasa left half plane yun. Number of poles sa left half plane equals 1. Kasi nga dapat tatlo yung closed loop poles natin. Okay? Okay. So we verify with MATLAB kung tama yung results na nakuha natin. So again, tandaan natin na based sa Route-Hurwitz criterion, nakakuha tayo ng dalawang pole sa um, right half plane, tapos isang pole sa left half plane. Okay. So ginawa natin, kinuha muna natin yung ating forward transfer function. Okay. So ito yung magiging forward transfer function natin. 1,000 over s plus 2 times s plus 3 times s plus 5. Okay. And then using feedback, okay. Kinuha natin yung closed loop transfer function which returns na ito. Okay. And then we computed for the pole. Okay, for the poles of the closed loop transfer function, in which case it would return negative 13.4136 at saka 1.706 plus or minus 8.5950 j. So nakita natin na yung real part ng ating dalawang complex pole ay positive. So therefore, that puts them at the right half plane of the poles. So mabe-verify nyo yun kapag apply natin yan using PC map. So ito siya. Okay, so ito yung dalawang poles niyo sa right half plane, ito yung sa left half plane. Verifying yung results na nakuha natin sa ating Route-Hurwitz criterion. Okay? So, ayun. Again, ano ulit ang Route-Hurwitz criterion? Can someone state ano yung Route-Hurwitz criterion? Wait lang. Ayo. Ngayon ko lang nabasa yung question ni, ito pala yung question kanina ni Mr. Villacorta. Okay, ngayon ko lang nabasa pala. Address lang natin. Bakit di daw nakatapat yung ano, yung A3, A2, A1, A0 sa S3, S2, tsaka sa S1? Sorry hindi, ngayon ko lang nabasa to. Ganito, pag gumagawa kayo initially ng route table, ang pini-fill up lang natin is yung first two rows. Okay, ipi-fill up lang natin is yung first two rows. Merong ano yan, merong algebraic ano yan, merong algebraic principle yan. Medyo yung derivation ng route table, hindi ko na i-discuss dito. Pero merong ano yan, merong basis yan sa algebra. Okay? Basta ang rule natin is ang i-fill up lang natin sa yung first two rows. Okay? So, ang pag-fill up is yung ito tapos ito. And then magko-proceed kayo doon sa next column. Okay? So hindi talaga siya tatapat. Hindi natin itatapat yung coefficients doon sa doon sa eksaktong power niya. Okay? Ang gagawin natin is i-fill up lang natin yung first two rows niya. Okay? Again, ang hindi natin objective sa route table na i-solve yung mga roots. Okay? Ang objective natin is alamin kung ilan yung roots na nandun sa right half length. Okay? So, ayun. Kaya hindi natin siya tinatapat. Dahil yun yung ito yung nire-require ito yung nire-require nung method. Okay? Medyo hindi ko na ipapaliwanag kung paano yung tawag ito, yung mathematical basis niya. Okay, yung basis sa algebra. Pero pwede kong i-forward sa inyo yung paper ng ng route table, kung paano na-derive yung route table. Okay? Kaso pag pinag-aralan niyo doon, maguguluhan lang din kayo. Okay, kaya ayun. So sa ngayon, medyo tanggapin lang muna natin na ganito yung rule na ginagamit. Pero meron niyang basis. Okay? Okay ba tayo doon, Mr. Villacota? Okay. Sorry medyo ngayon ko lang nabasa yung message mo kasi medyo delayed dumating. Actually, kung titingnan niyo dito, marami na kayong pumasok na messages. So ito lang yung pumasok na messages sa akin. Okay. Actually, binabasa ko lang yung messages niyo galing dun sa phone ko. Okay, so ayan. Yun. So balik ako sa tanong ko. Okay. Pero yun ang tandaan natin pini-fill up lang natin yung first two rows. Okay? Hindi na siya tinatapat talaga, pero pini-fill up natin yung first two rows. Okay? So ayun. Ngayon, balik ako sa tanong ko. Ang tanong ko is ano ulit yung Routh-Hurwitz criterion? So, Routh-Hurwitz criterion, the number of sign changes is equal to the roots of the polynomial sa right half plane. Okay, so very good. Yun yung eksaktong statement ng Routh-Hurwitz criterion. Okay? The number of sign changes is equal to the right half plane roots of the polynomial. Okay? So, ayan. Now, let's continue. So, ang conclusion natin ngayon dun sa ating is that your system is unstable. Okay. So, mabe-verify niyo 'yan kapag kinuha natin yung step response ng ating T. So, step T. Okay. Makikita natin na unstable siya kasi as your time progresses, makikita natin na lalaki siya. Okay. Palaki ng palaki yung ating response. Okay. In fact, may question, Miss Kaya? Tayin natin yung question niya. Pagkaano? Okay, tuloy natin. Punta yan na ito sa 10 raised to 25. Okay, so makikita natin yung scale nung natin is 10 raised to 25. 30 seconds pa lang yan. Okay, so or sabi natin mga 40 seconds plus. Okay, so unstable talaga ito. Okay? So, ayun. Now, let us make a route table for the following polynomial and tell how many
how many roots are in the right half plane and the left half plane. So, ito yung ano natin, ito yung polynomial natin. Okay, so we start off um, by the first two rows. So, since s raised to 7 ito, okay, since this is s raised to 7, uh, simula tayo ng s raised to 7 dun sa ating table. Okay, and then we fill up the first two rows. So, 3, 9, 6, 4, 7, 8, and 2, 6. Okay. Now, um, what would happen is, that pag kinompute natin si ito, that should be 9 times 6 minus 3 times 4 divided by 9.
Okay, you might be wondering bakit ganyan yung ginawa ko. Again, ang explanation ko dyan is that yung pag-evaluate ko ng determinant, baliktad na. Instead na gawin ko yung 3 times 4 minus 9 times 6, which is yung correct way of evaluating determinants. Tapos at saka ko siya in-negative. Ginagawa ko kapag nag-evaluate ako ng route table, baliktad yung pag-evaluate ko ng determinant. Therefore, pwede ko nang i-ignore yung negative part nung yung negative determinant niya, yung negative sign niya dun sa Okay? So tandaan niyo negative kapag nag-evaluate tayo ng determinant niyo para sa route table. Okay? Negative ito. Okay, negative itong part na to. Okay, negative itong part na to. So ginagawa ko, tinatanggal ko na yan, pero baliktad ako mag-evaluate ng determinant. That is why, ang nangyari dito, it's 9 times 6. 9 times 6 minus 3 times 4 divided by 9. Okay, maliwanag ba yun? Okay, so sige, tuloy natin.
Okay? So, we have 14 over 3 or 4.6667 nga. Okay. So, actually, kapag may decimal, dalawang choices natin. Okay, dalawang choices natin. Either i-turn natin ito sa isang whole number by multiplying this with a certain number that would make them whole number. Halimbawa ito, pag multiply natin ito ng 3, magiging 14 to. So, okay yun. Kasi positive number naman yung pinag-multiply natin. Again, you can multiply or divide any row by a positive number. Okay, or a positive integer. Okay. So, pero in this case, pwedeng iwanan na lang natin siya as is. Okay. Basta ang importante, siguraduhin niyo lang na hindi mababago yung sign nung nasa unahan. Okay, kasi halimbawa lalo na kapag masyadong maliit ito. Okay, pag masyadong maliit 'yan, it is possible that yung rounding off error niyo can actually change signs. Okay, so dapat careful kayo dun sa rounding off nung mga ganito, nung ganitong part dahil yun na nga, baka mabago niyo yung sign accidentally. Okay, kailangan hindi mabago yung I mean when I say mabago yung sign yung sa computations kailangan eksakto yung yung pagko-compute niyo so that the sign wouldn't be affected. Okay, so ayun. Kaya okay lang naman na naka-decimal siya. Okay, okay lang na naka-decimal siya. Pero careful lang kayo sa pag-round off. Okay. So recommendation ko is 4 decimal places or 4 significant figures para hindi para medyo safe. Okay. So ito na nga yung 4.667. Okay. So next, ito can be obtained by this is 9 times 7 minus 3 times 8 divided by 9. Okay. So that should give you 63 minus 24 divided by 9. So that's 4.3. Okay. And then obviously ito, okay, this one is 0 kasi yung okay, hindi pala obviously 0 to kasi pero this becomes that becomes 9 times 2. Okay. Minus 3 times 6. Okay, divided by 9. And this is 18 minus 18. So 0 yun. Kaya magiging 0 to. Okay. And then, ito yung sinasabi kong 0 na. Okay. Ito yung sinasabi kong 0 na kasi yung kasunod niya dito, 0 na rin. So, that's 9 times 0 minus 3 times 0. Okay. Again, mapapansin nyo na yung instead na ang determinant ko is 3 times 4 minus 9 times 6. Okay, ginagawa ko siya 9 times 6 minus 3 times 4 kasi nga, tinitake into account ko yung negative determinant. Okay? So, kaya nakabaliktad kaya kung nagko-compute kayo ng determinant, medyo baliktad yung ginagamit natin dito. Dahil nga, ina-account natin na negative determinant siya. Okay? So, ayan. Now,
Question, how do I compute yung first column dun sa S raised to 4 na S raised to 4 the row? Paano natin ko-compute nito? How do we compute yung first column S raised to 4 row? Anyone? So, we multiply yung 4.6667 times 4, okay, minus 9 times 4.333 divided by 4.667. Okay, so yung kay Mr. Dasalya, grouping lang ito. Medyo kailangan i-grupo mo lang ng konti yung numerator. Okay? So that's how we compute them. Okay? So, sige, tuloy natin na. Ito yung sinasabi kong, sige, mamaya na pala. Ito muna, 9 times ito, okay. So, ito tsaka to, tapos ito tsaka to, para ma-compute natin to. Okay, so this should be 4.6667 times 4 minus 9 times 4.3333 divided by 4.6667. Okay. So, pag in-compute natin yan, that becomes 4.6667 times 4 minus 9 times 4.3333 divided by 4.6667. That should give you negative 4.357071. Okay. So, ayan. Okay. Then, next ito. Ito yung sinasabi ko sa inyo na kapag ka 0 naman ito, pwedeng ito, ibaba nyo na lang dito. So, since 0 naman to, ito, pwede nyo ibaba yan. Kasi ganito ang mangyayari dyan. That becomes, ang computation yan is 4.6667 times 8 minus 9 times 0 divided by 4.6667. So, magsisira naman to, so magka-cancel ito. Kaya may iwan doon 8. Okay, kaya ito rin yung magiging 8 dito. Okay, so kapag ka 0 na yung nasa ilalim nun, pwede nyo ibaba yan. Katulad nito, ganun din to eh. 9 ito, tapos ito, tsaka to. So, since ito 0 itong nasa ilalim, ito ngayon, pwede nyo ibaba dito. Okay? So, ayan. Now, you just need to complete this table to verify na ito nga yung magiging values or close to
that yung magiging values ninyo. Okay. And then from there, let's count the number of sign changes. Okay. So yung number of sign changes natin is ito, isa, from positive to negative. So isa, then dalawa, then tatlo, then apat. So you have 4. Number of sign changes, you have 4. Okay. So therefore, number of right half plane poles, number of poles at the right half plane, that would be 4. And the number of left half plane poles or roots dito kasi polynomial na pinag-uusapan natin. So that would be 3. Kasi 3 dahil 7 ito eh. So we are expecting na meron tayong 7 roots. Okay, so yung 4 to nasa kanan, yung 3 na nasa kaliwa. Okay, pwede nyo ring i-verify yung location yan. Okay, using roots function sa roots function sa MATLAB or sa Octave. So input nyo lang dito yung array nung coefficients. Okay, so ayun, may verify nyo yung roots. Then may verify nyo na 4 doon ay may positive or located sa right half plane, yung 3 doon located sa left half plane. Okay. So that's for your basic route table. Okay. So sa next topic, pag-aaralan natin yung mga special cases ng route table niyo.
May questions so far regarding dun sa natin? Regarding dun sa basic route table. That's basic route table, ha? Okay. Naintindihan ba yung part na yun? Okay, so dalawa lang yung nag-respond. Ibig sabihin, hindi naintindihan ng iba. 3, 4, 4 na. 5. Okay, so 5. Okay, anyway, so let's continue on sa pag-discuss nung special cases naman ng route Hurwitz criterion. So, diyan malalaman ano yung sinasabing special cases. Okay. Okay. So, now we proceed with the special cases of your route Hurwitz criterion. Okay, in which dalawang special cases yung pag-uusapan natin. Okay. Number 1 is that the route table can sometimes will have a 0 only in the first column of a row. Okay, so sa isang row, yung first column nun magsi-0. Okay? So naging special case yun kasi kung maalala nyo, lahat ng yung elements natin sa first row, ginagamit natin as a divisor para makuha nyo yung next row. Okay? So kapag ka nag-divide by 0 kayo, syempre magkakaroon ng problema doon. Okay? Or number 2, the route table sometimes will have an entire row of zeros that consists of will have an entire row that will consist of zeros. Okay. So, yun yung dalawang special case na pag-uusapan natin. Okay. So, for the first one, 0 only in the first column. Okay. If the first element of a row is 0, okay, division by 0 would be required to form the next row. Okay. To avoid this phenomenon, an epsilon or this symbol, okay, is assigned to replace the 0 in the first column. Okay, then the value of epsilon is then allowed to approach 0 from either the positive or negative side, after which the sign of the entire of the entries in the first column can be determined. Okay. So halimbawa meron tayong case dito. Okay. So let's determine the stability of the closed loop transfer function of this one. Okay. So kapag tiningnan natin yung ating route table for this one. Okay. So we will have okay, so we will have 1, 2, 3, 6, 5, 3. Okay, as yung coefficients ng natin, ng ating closed loop transfer function. Okay. Now, so evaluating ito, okay, we will have 2 times 6 minus 1 times 3. 2 times 3. Okay, minus 1 times 6.
divided by 2. So this is 6 minus 6 over 2, that's 0. Okay. Then bago kayo bago kayo conclude, okay, ng either itong first case o second case, tingnan niyo muna yung susunod na element. Okay, so yung susunod na element diyan is 2 times 5 plus minus 1 times 3 divided by 2. So that should give you 10 minus 3, that's 7 over 2. So ito yung 7 over 2. Okay, and then obviously itong pangatlo to is 0 na. Okay. So in which case, meron kayong 0 on the first column. Okay. So kahit na 0 ito, okay, ito hindi to 0, non-zero ito. So this falls under the 0 only in the first column case. Okay. So ito yung first special case na gusto nating itake. Now, ang problema nga nito is that kapag 0 ito, yung next row natin is evaluated by dividing 0 dun sa ating elements sa next column. So that would not be possible. So ang gagawin natin is that we replace that 0 with a number called epsilon. Okay, yung epsilon na yan is made to be a very very small number. Okay, a very very small number. Now either siya ay positive or siya ay negative. Okay. So tingnan mo natin ano mangyayari kapag naging epsilon yan. So we will evaluate now ito as 6 epsilon, okay, minus 2 times 7 halves, so that is 7, divided by epsilon, okay, and then ito, okay, again, this would be 3, again, this is 2 epsilon, tapos 3, tapos 0, so ito, pwede natin i-carry over dito, okay, so next, we will have, ito yung medyo complicated dito ng konti, no? So we will have 6 epsilon minus 7 divided by epsilon, okay, times 7 over 2, okay, minus 3 epsilon, okay, divided by 6 epsilon minus 7 divided by epsilon. So pag in-evaluate natin siya by some algebraic manipulation, makukuha natin ito. Okay, so paki-verify na lang kung tama. Okay. And then, of course, this is 0 na dahil 0 itong dalawang to. Okay, and then 0 din to dahil 0 na yung kasunod niya. And then, finally, para dito, we will have this to be carried over here. Kasi nga, ito, at saka ito. Ito, tsaka to, 0. So, ito, pwede rin ibaba dito. Okay. So, now, we are now able to evaluate yung first column. Okay. We are now able to evaluate itong first column natin. Okay, so what would happen then is that itong epsilon, papalitan natin siya ng very small positive or negative number. So, kukunin natin yung first column ngayon dito. Okay, and then tingnan natin ngayon, what if this is a very small number na positive? So, positive siya. I-assume natin na yung epsilon natin is positive. Now, if this is a very small number, itong 6 times a very small number would be actually very small. Okay, so you can imagine na itong epsilon nyo is actually, halimbawa, positive 0.0001. Okay. So, pwede nyo gamitin nyo to evaluate here. Okay. So, halimbawa, 6 times positive 0.0001 minus 7 over ito. Okay. It would turn out na pwede rin i-check yan using your calculator. So, yan. So, ginamit natin yung calc function. Okay. So, tinamit natin 6x minus 7 over x. Calc 0.00001. Okay, turns out na negative siya. Okay. So lalabas ngayon negative itong negative siya. Okay. So pwede niyo gawin 'yung sa mga susunod. Okay. By assigning a certain small number dun sa ating epsilon. Okay. So then malalaman natin na yun na nga positive negative to. Tapos ito magiging positive, ito positive. Okay. So we will find out na meron two sign changes. So we will have a sign change here, from here to here. Okay, and then from here to here. So you have two sign changes. Okay. Okay. So kapag ginawa niyo siyang negative, ganoon din, makakuha rin kayong dalawang sign changes. So kung negative ito, sabihin natin gawin niyo yung negative 0.00001. Okay. So dito pa lang, from here to here, magiging negative na siya kasi nga negative yung inassign yung number. Pero pag kinompute nyo yung next, magiging negative, magiging positive na siya. And then ito, magiging positive na rin and so on. So, magiging dalawang sign changes na yan. Okay, so either yung epsilon nyo is positive or negative, you will have two sign changes, and therefore there will be two sign changes. So the number of sign changes is 2. Therefore, the number of poles at the RHP is 2, and the number of poles at the LHP is 3. Okay? 3 kasi dapat yung number of poles sa RHP tsaka sa LHP all in all dapat maging 5. Dahil S raised to 5 yung pinakamataas nating degree. Okay, so you will have that one. Now, so medyo napansin niyo na medyo hindi ganoon kadaling na maglagay ng epsilon kasi nga nagiging algebraic siya. Okay. So para numerical pa rin yung solution niyo. Actually, in the evaluation of the route table or kapag in-evaluate itong route table, pwedeng ito directly palitan niyo na to ng number na maliit. Palitan niyo na kagad siya ng 0.0001. Okay? Instead na gawin niyo pa siyang epsilon. Kaya lang, dalawang beses natin gagawin ito. Isang positive, isang negative. Okay? So, ayun. Halimbawa, ito na ngayon natin, yung ating route table. Sinimulan ko na siya. Okay, so 1, 2, 3, 6, 5, 3. So again, pagka kinumpute natin ito, okay, itong part na to, this becomes 0. Okay, pero in this case, instead na 0 yung epsilon ipapalit ko sa kanya. Ipapalit ko sa kanya is 0.0001 instead. A positive small number. Okay, so that pag kinumpute natin ito ngayon, that becomes 0.0001 times 6, okay, minus 2 times 3.5 divided by 0.0001. So that should become negative 63,994. So yun yung lagay natin dito. So let us make this as negative 63,994. Okay, and then ito magiging 3 na to kasi ito i-bring down na lang natin to dito. Okay, again 0 kasi ito. Okay, now in this case this becomes that should become negative 63,994 times 3.5, okay, minus 3 times 0.0001 divided by 63 or negative 63,994. That should give us 3.5. Okay, positive 3.5. So you would have 3.5 here. Okay, and then ito ay 0. Okay, this is 0. Dahil 0 itong dalawa, so 0 ito. And then this becomes 3. Okay, so from there, makukuha natin ngayon na meron tayong isa. Okay, and then dalawang sign changes. So the number of sign changes na meron tayo, equals 2. Okay, so therefore the number of right half plane poles, okay, is 2, and then the number of left half plane poles is 3 kasi 5 itong ating highest degree. Okay. Now, ang gagawin nyo ngayon is uulitin natin yan, but this time, this is negative. Okay? This is negative now. Okay?
Bago ko ulitin yun, nakuha nyo yung part na instead na epsilon ang ipalit natin, small number na lang talaga kagad ipapalit natin. Okay, so pwede na kasi nga ang problema ko nga dun sa isang method, dun sa method na prinasent ng libro. Dahil nga may epsilon siya, medyo magiging algebraic yung yung pag-compute dun sa So medyo magmo-multiply ka pa ng mga merong symbolic variable. Anyway, kung magagamitan niyo naman siya ng Octave o ng MATLAB using yung symbolic package or symbolic math toolbox ng MATLAB, wala naman din magiging problema. Okay, kaya lang, sabi ko nga, para tuloy-tuloy na numerical din yung solution niyo, instead ng epsilon ang ipalit nyo na lang is a very small number. Okay? So, Kaya lang, yun nga lang, dalawang beses yung gagawin to. Isa kapag positive yung small number ninyo at isa pag negative. Okay, so tingnan natin ngayon sa sunod. So tingnan natin. Okay. So in this case, again, papalitan natin to ng yung 0 dito. Okay, papalitan natin ng negative 0.001. Okay. And then still this is 3.5. So ngayon pag kinompute natin ito, that should become negative 0.0001 times 6 minus 2 times 3.5 divided by negative 0.0001. That should give us 70,006. So, dapat ito maging 70,006 ito. Okay, so this is 70,006. Okay, and this one is still 3. Okay, kasi mabibring down natin siya dito. Okay, this one, okay, becomes 6 times 3.5 minus 3 times negative 0.0001 divided by 70,006. That should give us 3.5 din. Okay, so this is 3.5. This is 0 and then this is 3. Okay. So again, counting the number of sign changes, you would have 1, okay, and then 2. So you still have the number of sign changes, okay, to be 2. Therefore, the number of right half plane poles is equal to 2, and the number of left half plane poles equals 3. So ganun pa rin. Okay. So whether we change it with a positive or negative number, yun yung natin, yun yung makukuha natin. Okay. And still, instead of changing this to epsilon, directly palitan niyo na siya kagad ng small number. Okay. So it won't una, mas madali ito dahil numerical pa rin yung solution niyo. Okay. That's number 1. And number 2, it doesn't change yung yung ating results. Okay. So yun nga lang kapag ganito, pwede palitan niyo siya ng positive tsaka ng negative number para sure kayo na dalawa lang yung na pareho yung results niya. Okay. Now, paano pagka hindi pareho? Actually, napakadalang nung case na hindi yan magpapareho kasi syempre fixed naman yung location ng poles niyo. Okay, hindi naman nagbabago yung location ng poles niyo. Depende diyan sa epsilon. Okay. Kumbaga, pag binigay sa inyo yung polynomial, fixed na yung location ng poles niya. So, supposedly dapat hindi mabago yan. Okay. So, I don't know kung merong case na yan ay nababago. Okay. Although there is still this very small possibility na baka mabago siya. Especially kung medyo alanganin yung location ng isang pole. Lalo na kung nasa gitna talaga siya. Okay. Or yung malapit talaga siya sa gitna. So baka pwede. Okay. Pero as of now, sa tagal nating tinuturo itong hindi pa naman ako nakaka-encounter ng na nagpalit ito ng results. Okay. Or yung mga ganitong case nagpapalit ng results. Okay. So that's one way we can solve this We can solve this case na meron tayong 0 only in the first column. Okay. So ayan. May alternative diyan. Okay. May alternative way of actually solving that case. Okay. That is we obtain a polynomial that has roots reciprocal of the original polynomial. Okay, which may not arrive at a route table with a 0 only in the first column. Okay, so ang gagawin natin is ganito. Kung meron tayong polynomial, okay, at meron siyang roots, okay. Pag kinuha natin yung reciprocal ng roots natin, hindi naman napapalitan kung nasaan nakalocate yung poles natin. Yan. For example, real poles man tayo, pero this also applies to imaginary poles or to complex poles, okay. Pero sa real poles, kapag ka meron kayong say pole sa negative 2 tsaka negative 3. Pag kinuha niyo yung reciprocal nitong pag kinuha niyo yung reciprocal nitong negative 2, that becomes negative 1 half. Okay. Kasi pag kinuha niyo yung reciprocal nitong negative 3, that becomes negative 1/3. Tama ba? Okay. Now, mapapansin niyo na negative pa rin sila. So, ibig sabihin, hindi siya nagpalit ng location. Ay, nagpalit siya ng location pero hindi siya nag-crossover sa right half plane. Kumbaga, nandito pa rin yung negative 1 half tsaka negative 1/3, nandito pa rin sa right half plane. Okay, so ito yung negative 1 half ninyo. Ito yung negative 1/3 ninyo. Nasa left half plane pa rin siya, sorry. Nasa left half plane pa rin siya. Okay. So, pero what happens kapag ang kinonsider natin is itong reciprocal ng roots ninyo. Okay. Tingnan natin muna ito. Kung ang roots ng polynomial ninyo ay negative 3 tsaka negative 2, yung polynomial that would result to those roots are s plus 2 at saka s plus 3. Okay? So, verify natin na itong s plus 2 at s plus 3 would give rise to the roots negative 3 at saka negative 2. In which, pag minultiply natin to, this becomes s square plus 5s plus 6. Okay? Pero, pag tinignan natin itong polynomial na panggagalingan ng mga roots na to, that should be coming from s minus 1 or s plus 1 half at saka s plus 1/3. Okay, in which pag minultiply natin yan, that becomes s square plus 1 half plus 1/3. Okay, pag inad natin yung 1 half at saka 1/3, 1 half plus 1/3, that should be 6 ang LCD. So this is 3 plus 2. 3 plus 2. So that should give us 5 over 6. Okay. So this is 5 over 6s plus this is 1 over 6. Okay. Or pag minultiply natin ito sa 6, basically. Okay. Pag minultiply natin ito sa 6 para ma-eliminate yung mga fractions. Okay. This becomes 6 s square. Okay. Plus 5s plus 1 over 6. Okay. Ngayon, pansinin natin ito at saka ito. Okay. Anong mapapansin natin sa coefficients nila? Ayun. Ayun. Anong mapapansin natin sa coefficients nila? Anyone? Yung isa, s square plus 5s plus 6. Yung isa, 6 yung numerator lang tingnan natin 6 square, 6s square plus 5s plus 1. Ano yung mapapansin nyo sa coefficients ng dalawang polynomial na yan? Anyone? Tapos, so yung 6 daw napunta sa s square. Tapos, ano pa? Yung constant kaya nangyari? Saan napunta? Yung constant nito napunta dito. Ito kaya yung constant nito saan nanggaling? So anong masasabi niyo doon sa coefficients ng dalawa? Nagpalit sila. Okay, so tingnan niyo to ha. Mapapansin niyo na kung ito, kung isusulat natin sa array yung coefficients, so that is 1, 5, 6. Okay. Ito naman kung isusulat natin sa ignoring the denominator
Okay. Kung isusulat natin sa sa array yung ano nito, this is 6, 5, 1. Okay. So, ang papansin natin na yung inyong coefficients, okay, pag in-arrange natin yan in reverse, okay, in reverse, yung roots nun, okay, would actually be the reciprocal of the roots of the original polynomial. Okay. So, ito yung isang technique na pwede natin gamitin ngayon dito. Ang gawin natin is, isulat natin itong denominator nyo, okay, instead, using the reverse coefficients. Okay. So, in that way, makukuha natin yung location ng reciprocal ng roots. And again, kung yung reciprocal ng roots nyo naman is, hindi naman nababago yan kung nasa left half plane siya o nasa right half plane siya. Okay. So dito, kung ito yung binigay sa ating, ito yung binigay sa ating denominator, okay, in which ang ating coefficients ay, ang ating coefficients ay 1, 2, 3, 6, 5, 3. Okay. Sulat natin siya ngayon as yung reverse niyan. Okay. Which is 3, 5, 6, 3, 2, 1. Okay. So, yan yung susulat natin ngayon. Or yan yung ilalagay natin ngayon sa route table natin. Okay. So, in which case, we will have the following. So, ayan, 3, 5, 6, 3, 2, 1. Okay. In which, kapag pa-verify na lang, na kapag kinumpleto nyo yung route table, wala kayong may encounter na 0 only in the first column. So, kapag gano'n, mas maganda. Pero, don't, possible pa rin na mag-0 only to on the first column. Posible pa rin yan na kahit baliktarin nyo siya, ganoon pa rin yung mangyayari. Okay? So, ayun. Pero in this case, hindi kasi nangyari yan. So, mas maganda. So, dito, mababasa natin na meron pa rin 2 sign changes. So, meron tayong dalawang sign changes dito. Okay, so ito, tsaka ito. Okay, so, merong 2 sign changes. Okay, meron 2 sign changes from here to here, tapos from here to here. So, yung number of sign changes natin is still 2. So, ibig sabihin, number of right half plane poles natin is still 2. So, yung number of left half planes pa rin natin is 3. So, papansin nyo, doon sa tatlong methods na ginamit natin, pare-pareho yung nakuha nating conclusions. Okay? So, that is meron siyang dalawang right half plane poles sa tatlong left half plane poles. Okay? So, yun yung mga methods ngayon na pwede nyong gamitin. Okay? Para ma-evaluate kung sakaling magkakaroon ng entire row, magkakaroon ng 0 dun sa first column ninyo. Okay? Una, epsilon. Pangalawa, magpalit kayo ng very small positive at saka very small negative number. Pangatlo, i-reverse nyo yung coefficients ng polynomial ninyo. Okay, so those are the 3 methods na pwede nyong gamitin para ma-solve yung yung ating route para makompleto nyo yung route table para dun sa ating 0 on the first column. Okay? So, yun.
Okay. So, yung next part niyan, which is makikita nyo, 36 minutes pa. Okay, yung next part niyan is would discuss yung yung second special case ng route Hurwitz ng route table in which yung entire row ninyo ang magsi-0. Okay? So in that case, I would like you to continue watching this para dun sa case na yon para maaral nyo ano mangyayari kapag yung entire row ninyo magiging 0. Okay? So, ayun. Kasi kapag pinapanood pa natin, 10 minutes na lang kasi yung ating time. So, syempre, obviously, hindi tayo abot para hindi natin abutin 'yan para matapos. Okay. So, ganito. So, I'll just dedicate the rest of the time para sa mga konting announcements. Okay. So, announcement number 1, yung inyong quiz number 2, meron pa ring mga violations in terms ng ng file naming. Okay. So ngayon naman, ang nangyari is, 'di ba pinalagyan ko na ng question code tapos no answer. Marami naman sa inyo tinanggal naman yung question code. So ang sinunod naman nila yung unang instruction. So hindi ko alam kung saan ko na ilalagay yung sarili ko. Yung ano ko, yung tawag ito, yung code ko or yung Microsoft Flow ko na ginagamit para mag-segregate ng mga files ninyo, wala na, hindi ko na magamit kasi nga wala namang sumusunod sa inyo or marami sa inyo nagva-violate pa nung file naming convention. Kaya medyo nahihirapan na rin akong maghiwa-hiwalay ng files. So bahala na. Basta i-apply pa rin natin yung deductions. Okay? So para doon. Okay. That's number 1. Number 2, may homework na kayo para dito. Ang mangyayari pala is yung quiz number 3 ninyo mamumove ng schedule kaysa dun sa nakalagay sa ating original schedule. So parang mamumove yata siya ng October 28 yata. Hindi ako masyadong sure. Pero i-announce ko na lang some other time. Okay, parang mamumove siya ng October 28 kasi yung deadline nung inyong parang October 27. Okay, pero ang mangyayari doon is 2 topics lang yung masasakop noon o 2 homeworks lang yung sasakupin nung quiz number 3 ninyo. Okay, so yung ngayon itong stability, tsaka yung next topic which is steady state error. Yun lang yung sasakupin yan. Although magbibigay pa kasi ako ng isa pang topic, kaya lang yung topic na yon nasa nasa quiz number 4 na. Okay? So makikita niyo naman based dun sa deadline ng mga homeworks. Okay? So ayun. So yung quiz number 3 niyo baka 2 topics lang yung sakupin. Stability lang tsaka steady state error lang yung sasakupin niyo. Okay. So yung quiz number 4 yun yung Tapos yung midterm exams niyo, hindi ko pa alam kung kailan pa natin siya i-schedule. So bali hintayin ko muna matapos yung nasa laboratory. Okay. Pero nakikita ko baka isabay na lang natin siya sa final exams. So, or hindi naman isabay, pero magkasunod. So, may midterm exams muna kayo, tapos meron kayong final exams. Okay. So, ang mangyayari doon is, kumbaga, parang may mga questions kayo na para sa midterm exams, tapos may mga question kayo para sa final exams. Okay. So, may mga certain topics naman na para lang sa midterms. Tapos may mga certain topics lang naman para sa final exam. So, basically, hindi naman sila maghahalo. Okay. So, parang isang tuloy-tuloy na exams na lang yung midterm at saka final niyo. Okay. Kasi kapag ginawa ko naman is wala nang midterm, finals na lang. 40% ng grade nyo kukunin ko doon sa final exams na yun. Baka hindi kayanin. Okay. So, tingnan natin. Pag-usapan natin sa mga susunod na mga araw. Okay. So, medyo malayo pa naman yun. Baka next week siguro pag-usapan natin mabuti. Okay. So, ayun lang. I-upload ko mamaya itong session natin and at the same time itong mga recorded lecture ninyo dun sa inyong playlist para mapag-aralan niyo na siya. Okay? So, may questions ba? Okay, wala. Tapos meron pala akong isang papagawa sa inyo. Medyo requirement kasi ito sa accreditation eh. So may papagawa ako, pero next week ko na i-announce kung ano siya. Pero basically, yung isang homework ninyo, halimbawa itong homework niyo tungkol sa stability, gagawa ako ng groupings. Ipapagrupo ko kayo. Siguro tatlo. Tapos, ang gagawin niyo is habang sinasagutan niyo siya, pinag-uusapan niyo yung sagot ninyong tatlo. Okay? So, sasagutan niyo yung homework tapos pag-uusapan niyo yung tatlo. Okay. Tawag natin doon is focus discussion group. So, meron kayong grupo na i-discuss nyo yung results nung isang homework ninyo. Okay. So, isang homework lang naman ko siya i-require, hindi naman sa mga susunod na. Kailangan lang natin siya para i-exhibit para sa ating accreditation. Okay, so next week i-announce natin yung mechanics para doon. Okay? So, pero ang requirement doon, sana nagawa nyo na rin yung homework number 3 ninyo. Okay? So, ayun. Yun na lang muna sa ngayon. Okay, so, I think we can dismiss. Okay? Thank you for attending today's meeting. Okay, so ingat kayo lagi.